Series Solutions of Differential Equations, Section 10.10 from the Edwards and Penny textbook. Ach, ich liebe die Serie und Infinitesimalrechnung. That's a quote from Leonhard Euler, who lived from 1707 to 1783. Recall linear second-order homogeneous differential equations with constant coefficients that we studied in section 8.6. They were of this form: a times the second derivative plus b times the first derivative plus c times the original function equals 0. And our strategy was to replace the second derivative with r squared, the first derivative with r, and the function itself with a 1. And then after solving that quadratic equation, there were 3 different cases, and we just had to identify the case and use the given formula for our solution. However, no such simple method exists for even simple-looking second-order differential equations if the coefficients are variable instead of constants. For example, y prime minus xy equals 0 has no solution that can be expressed as a combination of any known explicit functions. Let me expand on that. If we try to solve it by separating the variables, we end up with 1 over y times the second derivative equals x. But now what? We can't multiply by dx squared. That's not allowed. That's not a quantity we can separate. And so we're stuck. So we need another method. We will, however, solve this particular differential equation later on in this lesson by means of the new method. New method. We assume y can be written as a power series and then attempt to find a power series solution. Sometimes the solution will be a familiar series and we can rewrite our solution in terms of well-known explicit functions. Sometimes it won't quite work out that way. So here's the deal. We assume that y is a power series and write it this way. Y prime, then, you get rid of the c sub 0, that goes to 0, and then you take the derivative of each term and you get this power series. And then finally, since we're doing second-order differential equations, take the second derivative and c1 goes to 0, and you can take the derivative of the general term, or you can take the derivative of each of the terms in the expanded form. So we're going to use these 3 formulas in our method. Here's an example. Use series to solve y prime plus 2y equals 0, which we can actually already solve by separation of variables, but I just want to show you an easy one first. Alright, so there's my series for y prime and my series for y. And so I'm going to take the series for y prime and add 2 times the series for y, and that's going to equal 0. Okay, continuing. We're going to need both the series to start with a 0 so that we can combine them. And in order to do that, I just do a change of index so that if you'll compare, by taking n equal 1 down to n equals 0, I then have to up the n's in the formula and replace n with n plus 1 and n minus 1 with n. And so this is the same series, but I'm starting at a different index. Now I can combine them because I've got the same starting point, n equals 0. So combining into one series, we get the sum of the 2 coefficients times x to the n. And all of that has to equal 0. Now, the only way it's going to always equal 0 for all x values, because x doesn't have to be 0, means that to be true for all x values, all the coefficients have to equal 0. Otherwise, it's not going to be 0 for every x value. So we set the coefficients equal to 0 and solve for c sub n plus 1 in terms of cn, so that if I have one coefficient, I can figure out all the rest. Now notice that this is a first-order differential equation, and since we only have the first derivative, in our solution we're going to have one unknown constant, whereas if it was a second-order differential equation we would have 2 unknown constants. So the first constant is going to be the unknown one, c0. So here's our formula again. C1 is going to be negative 2C0 over 0 plus 1, or negative 2C0. C2 is going to be negative 2C1 over 2. Then we replace C1 with what it equals in terms of C0 and simplify. Now I'm going to leave it like that. You'll see why in just a minute. C3 is negative 2C2 over 3. Then we replace C2 with what it equals in terms of C0. So now we have C3 in terms of C0. And you can keep going until you see a pattern. Here's C4. See the pattern? I think you do. So our original series, again, there it is as a power series for our original function, and there it is in expanded form. And so we can factor out a C0 from all the terms and then just analyze what we had up there, which is pretty obviously, it's alternating positive negatives, so we have negative 2 to the n, and then on the bottom it's obviously n factorial, and so that's our coefficient. Now, you should recognize that series. If you don't, then you just leave the answers in terms of series. But that particular series, if you remember all your series from last year, or you can write them down and compare, this is a series for e to the negative 2x. So our final answer is explicitly y equals c0 times e to the negative 2x. Now let's check that, because as I said, this particular one is actually very easy to solve by separation of variables. Here's our original equation. We move the 2y to the other side, divide by y and multiply by dx, integrate both sides, raise both sides, take e to the both sides, or anti-log both sides, and then e to the negative 2x plus c you can separate into e to the negative 2x times e to the c, and then to get rid of the absolute value you've got two solutions, plus or minus. And so our c0 value is plus or minus e to the c. I mean, those are equivalent. They're both constants, right? So it checks. Okay, here's another example. Use series to solve the second order differential equation, which can also be solved by the method of 8.6 because the coefficients are constant. So here's our second derivative series formula and our regular function series formula. And so we add those together and set them equal to 0. Now this time that first indices is starting at 2, so we've got to change that to start at 0. And so we up our n's in the subscripts and so on by 2 to make it equivalent, just a change of indices there. Now we can combine those, and we're only looking at the coefficients because the sum of the coefficients then has to come out to 0. So I can solve for c sub n plus 2 in terms of c sub n. Second order differential equation means we're going to have two unknown constants in our solution. Okay, so there's our formula again. C2 is negative C0 over 2. C3 is negative C1 over 3 factorial. C4 is negative C2 over 4 times 3. Now, I've already got two unknowns, C0 and C1, that we're not going to solve for. So I replace C2 with what it is in terms of C0 and simplify. And then C5 is going to be in terms of C3, which I can then rewrite C3 in terms of C1. I didn't show all the computations, but you get the idea. So you keep going until you see a pattern. And sometimes you don't simplify it exactly, you know, in order to see what it is. But in this case, I did simplify it all the way down. So you can see that they're alternating, and it appears that we just have factorials on the bottom. So here's the general form for our solution again. And so we're going to replace the C0, C1, C2, C3, etc. with our new formulas. And 2, of course, is the same as 2 factorial, and C1 is over 1 factorial, C0 is over 0 factorial. I just didn't write it, so the pattern is maintained throughout. And so here it is in general series formula. Notice that you have to write it in terms of two different ones because you have C0 times the even powers of x, and you have C1s times the odd powers of x. And so that's how you rewrite it. Now, do you recognize those series? The first one is cosine x and the second one is sine x. So there's our solution, and that should look familiar. That's one of the forms we learned in 8.6. So let's check using our 8.6 method. There's the original equation. There's the quadratic that goes with it, r squared plus 1, which has two imaginary or two complex roots. That's case 3. And in this case, p is 0 and q is 1. And when we substitute, the e to the 0x becomes 1. And we do, in fact, get the same thing we got by using the series method. Here's another example. Use series to solve y double prime minus xy equals 0. And this one cannot be solved by previous methods, so we have to use series. So here's my double prime formula and my original function formula in terms of a power series. And so this time we have the first one minus x times the second one. So again, we need the same indices, so I change the first series to start at 0 by upping the ends by 2, and then I brought the x inside the second summation sign to make it x to the n plus 1. Now that's a problem. We need it to be n so that we can collect like terms. And therefore we're going to have to change to n equal 1, and we'll have to do the same thing in the first series as well. So now we change everything to n equals 1, but you have to do it a little differently. In order to get that 0th term in the first series, you just bring out the 0th term. Okay? So you've got the 0th term, and then you've got the series starting at 1 minus the second series starting at 1. And then that means you have to, since you're upping the indices on the bottom, you have to lower the ends inside the series formula. So now we can combine them. And notice that C2 is going to have to be 0 because x to the 0 is 1. And so the only way we're going to always have 0 is if that first term is 0. Now we can collect the coefficients, and I went ahead and solved for c sub n plus 2 in terms of c sub n minus 1. Notice that we're going to have two unknown constants in our solution. So again, since C2 is 0, every third coefficient is going to be 0 because they're going to be based on C sub 2. Because C sub 5 is n would be 3, and 3 minus 1 is 2. So every third coefficient is 0. And then for C sub 3, it's based on C0. C4 is based on C1. C5 is back to 0 again. C6 is based on C3, which can be rewritten as C0, and so on. I just did a whole bunch of them, not necessarily showing all the steps till I could see the pattern. Okay, so here's y in the general form and the expanded form. And all the C2 is going to be 0, and then every third one after that will be 0. And so now I'm rewriting all the coefficients in terms of C1 and C0, etc. Do as many as you feel comfortable needing. And so then we have C0 times the x values that are raised to powers that are multiples of 3, and then C1 times the x powers that are multiples of 3 plus 1. Now, you probably don't recognize these series because they are not explicit functions, and we certainly haven't studied them. They are, in fact, however, gamma functions. Gamma functions can be written as integrals, not as explicit functions that we're familiar with. Now, just in case you're curious, the gamma function is actually defined for all real numbers except negative integers and 0, and defined via convergent improper integral. So it's a little weird. It's gamma of t equals the integral from 0 to infinity of x to the t minus 1 times e to the negative x dx. We will not be studying these functions, but I thought you might be a little curious. Here's a graph of the gamma function. Number 10, use series to solve 2 times quantity x minus 1 times y prime equals 3y. Okay, so we got 2 times x minus 1 times a series for y prime. Then I brought the 3y over and rewrote y as its series, and then that equals 0. Well, now what are we going to do next? We got this x minus 1 thing. First, you have to distribute your 2x and your minus 2. So now we have 3 series. What's next? Well, we need those indices to all start at 0, right? Now notice that I didn't change the formula in the first one, but I did up the ends in the second one by 1. Now why is that? Well, that's because if I put 0 in for n in the first one, I get 0. And so actually it's still going to start at 1, and so therefore it's equivalent. Okay, and in the second one, we did decrease the indices underneath by 1, so we increased all the ends by 1 in the formula. Okay, so now we can combine, and there's the coefficients, which have to add up to 0. So now we solve for c sub n plus 1 in terms of c sub n, and we get this formula. And remember that we're going to have one unknown constant because it's a first order differential equation. So C0 will be our unknown constant. So here's our coefficient again, our formula for the coefficients, and we plug in 0 for n and get C1 in terms of C0. We get C2 in terms of C1, which then can be converted into terms of C0. And then C3 is in terms of C2, which we then substitute what C2 equals in terms of C0, and so on. Here's C4 in terms of C3, and then substituting for C3 in terms of C0 and simplifying. And now let's get organized and write them all out in expanded form. And you might not recognize these. I did factor out a C0. Maybe that'll help a little bit. Notice that we have 1 and then we have a negative, and then all the rest are positive. Does this look familiar at all? Do these coefficients look familiar? If you're an expert on series, you may have an inkling, but don't worry if you don't. Let's look at them again. We can rewrite this one, the numerator, we can rewrite it as a numerator of 3 halves times 3 halves minus 1 over 2 factorial. And that's equivalent. And this one can be rewritten 3 halves times 3 halves minus 1 times 3 halves minus 2 with a negative in the front over 3 factorial, believe it or don't. And so this is actually the binomial series for C0 times 1 minus x to the 3 halves. Now if you didn't know that, don't feel bad. You don't have to for this course. But this shows you that it's nice to be super familiar with various infinite series. For the binomial series, this particular binomial series only converges for x between -1 and 1. The radius of convergence is 1 unit. Now let's check, because this particular equation can be solved by separation of variables. So there it is written with Leibniz notation. And then we separate the variables and get 1 over y dy equals 3 over 2 times x minus 1 dx. Alright, so now we integrate and we get log of the absolute value of y equals 3 halves log of the absolute value of x minus 1 plus c. And then we can hop that 3 halves up and make it an exponent using a law of logs. And now we anti-log each side. So we end up with the e and the natural log canceling out, and we get the absolute value of x minus 1 to the 3 halves times e to the c. Now, e to the c is equivalent to c0. It's just a constant. And then we have a little issue with the absolute value, but notice that x is between -1 and 1. So that means x minus 1 is going to be negative. Therefore, if we switch that around and make it 1 minus x, we can drop the absolute value, and now it matches perfectly. Okay, number 14, use series to solve y double prime plus y equals x. Now this isn't even homogeneous. So we do need this new method for sure. So here's our second derivative series plus our original function series equals x. Now that x is going to be a little bit of a problem. First thing we got to do though is fix that indices there on the first series. Now what I'm going to do is a little different here. I'm going to write out the terms, collecting like terms. When n is 0, we get 2c2 for the coefficient in that first series and c0 as the coefficient in the second series. So combine those times x to the 0. Then when n is 1, we get 6c3 for the first coefficient of x, and then in the second series the coefficient is c1. So collect those and so on. So the coefficient of x squared is 12c4 plus c2 and so on. Okay, now that has to equal x. So all the coefficients have to be 0 except the coefficient in front of x, which has to be 1, right? Okay, so the coefficient in front of x has to be 1, but all the other coefficients have to be 0. So let's take a look at what we got here. For that first, for the coefficient of x to the 0, c2 has to equal negative a half c0. And for the coefficient of x, c3 has to equal 1 minus c1 over 6. And for the coefficient of x squared, c4 has to equal negative 1/12 c2, which is equivalent to positive 1/24 c0. And then finally, not finally, but all I'm going to fit on the page here is that c5 is negative c3 over 20, which reduces to c1 minus 1 over 120. Notice it's the opposite of the 1 minus c1 in c3 there. Okay, now do you see some factorials here? I do. So here are our coefficients again. C0 and C1 are unknown and are just by themselves, and then these other ones we've solved for. Now what we have to do is we have to group all the powers of x which happen to be even with C0, and then if we just take half of the odd ones, we can pull out a C1, and of course C1x is the first C1 term, and then we have a negative 1/6 C1, and then the next one's a positive 1 over 120 times C1, but then we also have in the numerator of the odd terms that 1, so we're going to have a separate parentheses for those, starting with x cubed. And the reason I have a blank there is because that doesn't remind me of any particular series. But if I add an x and subtract an x, now that should look kind of familiar. It's the opposite of a known series. It's the opposite of the one in the second parentheses. So those are going to be the same, except we have to subtract it the second time. So do you recognize them? Here they are in general form. So maybe that'll help. And of course we have that little extra plus x in the middle. Now do you recognize them? Of course you do. C0 times cosine x plus C1 times sine x plus x minus sine x. Now you can't solve that one with any of our previous methods. You're going to have to use series. Now notice that these series converge for all real numbers, so the radius of convergence is infinite. And the series is a valid solution for all x in the real numbers. Number 20. Use series to solve y double prime minus 4y equals 0, given that y of 0 is 2 and y prime of 0 is 0. So we have our second derivative series minus 4 times the original function series equals 0. And we need to change that index in the first series to 0. So we lower n to 0 underneath the summation sign and then add 2 to all the n's in the expression. So now we can combine and set our coefficient equal to 0. And then solving for Cn plus 2 in terms of Cn, we get this formula. Now remember, since this is a second order differential equation, we're going to have two unknowns, namely C0 and C1. So here's our formula, and we do some computations now. C2 in terms of C0, C3 will be in terms of C1, C4 will be at first in terms of C2, and then substituting for C2 the expression in terms of C0, we get C4 in terms of C0, and we get C5 first in terms of C3, and then finally in terms of C1, and C6 is going to be in terms of C0 after we do some substitutions. So let's get that organized and factor out our C0 from the even powers of x and factor out C1 from the odd powers of x. Now I did a little hocus pocus in that second equation, that second parentheses, so that you'll recognize the series. I divided by 2 and multiplied by 2. So now you have the powers of 2 matching the exponents in both parentheses. So do you recognize them? Maybe, maybe not. The first one is hyperbolic cosine of 2x, and the second one is hyperbolic sine of 2x. The 2 comes from the fact that we've got powers of 2 in the numerator. If those were all 1s, then we would just have hyperbolic cosine of x and hyperbolic sine of x. But the 2's become coefficients. Okay, so now we have our general form, but the problem also asks us to find the specific solution when y of 0 was 2 and y prime of 0 was 0. So y of 0 has to equal 2, which equals a cosh of 0 plus b sinh of 0, and cosh of 0 is 1, sinh of 0 is 0, and therefore a is 2. Furthermore, y prime would be 2a sinh 2x plus 2b cosh 2x. And putting 0 in for x, we're supposed to get 0. So we end up with 4 0 plus 1b has to equal 0, and therefore b is 0. So now we have our specific solution in terms of cosh and sinh. Now, of course, the 0 times sinh 2x is just 0, so we have y equal 2 cosh 2x. And if you like, you can rewrite cosh 2x in terms of the exponential function and get a nice pretty answer of y equal e to the 2x plus e to the negative 2x. Now again, this particular differential equation can be solved using the method of 8.6. So let's just run through that quickly to confirm our answer. We have r squared minus 4 equals 0, which means r is plus or minus 2, which is the first case, and there is the formula for the solution. And if we put in the r's, then we have 2 for r1 and negative 2 for r2. And if we plug in 0 for x, we are supposed to be getting 2 for the result, which means that c1 plus c2 is 2. And then here's the derivative of our solution. And when we put 0 in for x this time, we're supposed to get 0, which means c1 minus c2 is 0. Now, if we solve those two simultaneous equations, pretty obviously, we get both c1 and c2 equal to 1. And therefore, we do get the very same result we got in the series solution. Now, another aside. This is Johann Peter Gustav Lejeune Dirichlet, a German who lived from 1805 to 1859. Now, a Dirichlet series is any series of the form summation from 1 to infinity of a sub n over n to the s, where s is complex and a sub n is a complex sequence. Now, we're not going to study those, but I just thought you might be interested to know there are a lot more series around than just the little old ones we study. Here's another aside. This guy's name is Jean-Baptiste Joseph Fourier. Lived from 1768 to 1830. I'm not guaranteeing my pronunciation now. A Fourier series is a way to represent a wave-like function as a combination of simple sine waves. More formally, it decomposes any periodic function or periodic signal into the sum of a possibly infinite set of simple oscillating functions, namely sines and cosines, or complex exponentials. This is actually the field of study my dad was into, but I don't have a lot of knowledge. You may have to study these later on in life if you become a physics or math or engineering major. And finally, Pierre-Alphonse Lowrent, who lived from 1813 to 1854. I couldn't find a photo or a drawing of him. The Lowrent series for a complex function f of z about a point C is given by this formula, where the a sub n's are constants defined by a line integral. We'll study line integrals later on in this course. And there is the line integral. Goody. Oh, there's one more. I lied. This is one of my favorite mathematicians. I read his biography. It was fascinating. It's called The Man Who Knew Infinity, if you want to pick one up at the library. Srinivasa Ramanujan, who lived from 1887 to 1920. Srinivasa Ramanujan was an Indian mathematician and an autodidact who, with almost no formal training in pure mathematics, made extraordinary contributions to mathematical analysis, number theory, infinite series, and continued fractions. Living in India with no access to the larger mathematical community, which was centered in Europe at the time, Ramanujan developed his own mathematical research in isolation. As a result, he rediscovered known theorems in addition to producing new work. Ramanujan was said to be a natural genius in the same league as mathematicians such as Euler and Gauss. And the reason I highlighted infinite series in red is that was his specialty. All right, so we'll end with a joke. We have a little guy jumping around. He says, I love these dreams. Each jump is a little longer. Each push off the ground a little softer until I glide. Now he's gliding over the beach and gliding over the ocean, and he says, I hope this is a dream. Well, I hope your dreams in multivariable calculus come true and that you enjoy the course, and I'll see you next time.